Okay, so this video, we're going to talk a little bit about Lewis structures that we have touched on prior to in honors chemistry, but this is just going to help us get a little bit of a review here, moving into a new unit that we're going to talk about, which is shapes. Okay, so let me try and get myself situated here. I'm sorry. Okay, so let's refresh our memories here for a little bit. So the Lewis symbols and the octet rule is the first thing we're going to talk about. So let's just refresh. Valence electrons are the outermost shell electrons. And the Lewis symbol consists of the elements and their symbol that they have that's based off of the periodic table. Okay, so for example, sulfur is in group 6A, which indicates that sulfur has 6 valence electrons. And we'll notice that those electrons are represented by these dots here. So if I was to do a few examples here, starting with carbon, carbon's in group 4A. So I would do carbon symbol with the 1, 2, 3, 4 electrons around carbon. And then, sorry, I keep going the wrong way with my camera. And then fluorine is in group 7A. So I would do fluorine with its 1, 2, 3, 4, 5, 6, 7 valence electrons. So if we look at carbon, carbon has 4 lone electrons. So carbon can ultimately have 4 different things bond here, where fluorine could have 1 thing bond here. And then you have aluminum that has 1, 2, 3 valence electrons. And aluminum doesn't like to bond because it's not, or share electrons because it's a metal. And most of the time, all of our covalent bonds we'll talk about here in another video that deals with the bonding between these nonmetals. Now, this is just how these elements start based off of their electrons on the periodic table. But we know that the octet rule states that elements aren't satisfied unless they have 8 valence electrons. So the octet rule states that elements want 8 outer shell electrons. That is when they are the most stable, is when they have those 8, okay? So down here, you'll notice you can take a kind of a gander at what's happening here is that this will show you, so the one that we did was carbon, fluorine, and aluminum, but you'll notice since the periodic table is set up so nicely, we start to see a nice little trend with the valence electrons and the Lewis symbols. Okay, so that's the first part of review. The second part is ionic bonding. So we'll remember, if we can refresh our memory from honors chemistry, that ionic substances occur when metals, so elements from the left side of the periodic table, and nonmetals interact with each other, okay? So elements from the right side of the periodic table. So whenever you hear ionic bonding, you should automatically think metal, nonmetal. And in order for these bonds to form, the metal will have to lose their electrons. And since it's losing electrons, that ultimately means the only thing that the nonmetal can do is gain the electron from the metal. So if we're looking at what's happening here, ionic bonds are actually super strong because we have then an isoelectronic interaction happening. Basically, it's like a very strong positive charge and a very strong negative charge coming together, okay? So what ultimately happens here is sodium loses its 1 electron to chlorine, okay? And then sodium becomes positive and chlorine becomes negative. So you'll notice that we have these little lines here. Those little lines indicate the electronic interaction between the sodium and the chlorine, okay? And as we expand these things, so let's talk, sorry, I'm getting ahead of myself. So the reason why the ionic compounds are super stable and super strong is because of that opposite charge between the cation and the anion. So the cation is the metal and the anion is the nonmetal. So that's, I mean, think about when you have a magnet, right? When you get one side of the magnet and the other side of the magnet attracted to each other, it just like forms like a solid brick of magnet, right? Ionic compound bonding is exactly the same as that. The solid array, so like this image that we have right here, where the sodium and the chlorine are starting together, we refer to that as a lattice or a lattice structure. So that therefore, we're going to have this thing called the lattice energy, which is the energy that is required to completely separate 1 mole of solid ionic compound into its gaseous ions. So since these lattice structures are very stable, we are going to have to put in a lot of lattice energy in order to remove those to break apart those substances. So let's talk about the magnitude. So magnitude is like the size of the lattice energy of an ionic compound. It depends on 2 things. Well, 3 things really. The charge of the ion, so the higher the charge goes up, the stronger the bond, right? And that makes sense, right? Because if I'm increasing the charge, that means I'm transferring more electrons, which means the attraction is going to be greater. There's sizes. The size of an atom is very important. I want you to think about it. If you have 2 really small atoms, they can snug very closely together, right? Or if you have 2 very large atoms, they're not going to be able to snug very tightly together in their arrangement of their atoms. And we can use Coulomb's law to describe this. So if we're talking here, this up here is talking about the charges. So if I have 2 different things in a bond, Q1 and Q2 represents their charges. So we'll notice that Q1 and Q2 is in the numerator of this equation. So if Q1 and Q2 is large, right, that means the attraction between is going to be a very high attraction, which means the lattice energy is going to be extremely high. And then you'll notice that distance is in the denominator, so distance isn't going to have that much of effect. It's basically the charge is what we're going to focus on. Now, if the charges are the same for the elements, that means then yes, then I have to focus on the distance. Okay. So what this means is for a given arrangement of ions, the lattice energy increases as the charges on the ions increase and as their radii decreases. So if the radii is small, if you think about what needs to happen in order for something to be large in the denominator, this denominator needs to be small in order for this to be big, right? If this is large, that means this is going to be smaller. Okay, so let's do a practice problem here. Let's arrange the ionic compounds sodium fluoride, cesium iodide, and calcium oxide in order from increasing lattice energy. So basically what I'm asking is, who is going to require the most energy to remove sodium and to remove these 2 substances from each other? Okay, so let's start with their charges. So sodium is +1, fluorine is -1, cesium is +1, iodine is -1, calcium is +2, oxygen is -2. So right out the gate, we know calcium and oxygen, even without even looking at size of atoms, is going to need the most energy because it has the highest Q charge, okay? So calcium oxide is going to need the greatest lattice energy, okay? And since these 2 now have the same charge, the only thing that I can look at now is their size, okay? Cesium and iodine are further down in their row of the periodic table, so that means that they're going to be bigger. So they're going to need less lattice energy. So they're going to be all the way down here, which then means sodium and fluorine is going to go in the middle. So calcium oxide is going to require the most amount of energy to break them apart, where cesium iodide will need the least amount of energy. And that is it for this video. Thank you.